Okay, so today I'm going to solve another very popular problem, which is asked a lot by Amazon, and it's called container with most water. So here we can see all the companies. So as I said, Amazon has asked it 30 times in the last 6 months. It's not so popular with Google or Apple, but they still have asked it a couple of times as well. Um, okay, so previously solved it, so I'm just gonna solve it again from scratch and explain the logic of how the solution works. So the problem statement is the following. You're given an integer array height of length n. There are n vertical lines drawn such that the two endpoints of the ith line are I comma 0 and I comma height I, or height index that I. Sorry. Find two lines that together with the x-axis form a container such that the container contains the most water. We have to return the maximum amount of water a container can store. So here in this example, like graphically, we can see the two, right? The two vertical lines or the two heights that with the x-axis form a container, right? And in this case, they're colored red, those two vertical lines, because those are the pair of numbers which together make the largest container, right? So in the input, we have the array of heights, which of course are integers. So here 1 is represented by this one, 8 is this 8 vertical bar, so forth. And the expected output is 49, right? So 49 is the container's area, right? So in this case, it's highlighted by blue, this blue rectangle, which of course is shaded with blue because it's representing like the water level. Um, Perfect. So in this case, for example, um, it's 8 and 7. It's because between the the value 7 and value 8, there is 7 entries, right? So if we count, for example, 1, 2, 3, 4, 5. Oh, sorry, it's exclusive. So if we count from the 6, 1, 2, 3, 4, 5, 6, and 7, right? Um, there is, yeah, 7 values. Um, So that's why 7 times 7, right? Because this is the base, has length 7. So 7 times 7 is 49. Um, cool. So that's the example. And then this one here is also pretty simple. So the output is the expected output is 1, of course. Um, okay. So there's two approaches. So well, maybe there's more actually, but the first, let's say, more intuitive approach is not the most optimal one in terms of speed. So I am going to basically go over it, and I'm just gonna go here. I'm gonna copy this thing, these inputs here. So it's this. Just gonna give some space. Okay, perfect. So since we have to find right, two pairs that have created the largest container, we would, like in the let's say in our first approach, we will need to compare the entry to every other entry, right? So that means that we will have to search through 1 and 8, 1 and 6, 1 and 2, 1 and 5, so on and so forth. And for example, we will have to search 8 and 1, 8 and 6, 8 and 2, 8 and 5, so on and so forth. So we will basically need to, for every number in the array, we have to basically compute the area against every other number in the array. And then, of course, we will need to also keep track of a variable, for example, max water, which will store that value. which of course it will be the same as the area that we computed, right? And in terms of the area, like, since this implementation here will obviously entail like two like nested for loops, so we will need to first compute, of course, figure out the base, right, for the area, and then that will basically just be the j index minus the I index, right? And we will also need to compute the height. And then there's one important thing to notice here is that the height of the rectangle is bounded, or of the container, sorry, is bounded by the minimum height of the two heights we're examining, right? Of those two pairs. So, for example, here the height is bounded at 7, right? Even though we have this pair, because of course, like, if not, like, the container or the water will overflow, right? So it's bounded by the minimum height. So here we will need to say, then we'll have to say find min height, right? Which is basically the min between, so let's just call it height A and height B, right? Or we can just say, actually, so it's more explicit with our indexes, and index J, right? So that will be, and then after that, we will have to say area. So we will need to calculate the area, which will be base times min height, right? So we'll have to do this computation for every other element as we drew here. And that will basically entail that this implementation, in terms of the time complexity, will be big O of n, n squared, right? And in terms of space complexity, it will be constant time, constant space, right? Because we will just need to maintain one extra variable, which is going to store our maximum max container, right? But then, of course, this time complexity, which is quadratic, does not really scale with large inputs. And I actually forgot to go through the constraints here. So if we look at the constraints, for example, like here n, so the amount of heights can be between 2 heights and 100,000 heights. So that's actually quite a large input in its worst case scenario. So for example, if we hit 100,000 heights, or even 50,000, or 25,000, even 1,000, um, an algorithm which has this time complexity will be extremely slow. And basically, once if we were to go with this solution, our solution would time out and basically wouldn't pass that case. Um, so there's a much better, a much more efficient way we could solve this, which will basically transform um, this quadratic time complexity into linear, right? So if I just draw a small little graph, um, here's x and here is y. It's kind of like a horrible y, but so this n squared, bright orange. So this n squared will typically just look like this, right? And then if we have this linear, of course it will be a straight line. And what this basically means is that the time of the computation will grow linearly, with the size of the input. And in this case, this quadratic one will be quadratic in terms of the size of the input, right? So it will take much longer time, and of course, if we label the y-axis, this will be time. It will take much longer time, right? Um, okay, perfect. So let's go to the next better example. So I'm just gonna go here, um, and in this example, we can use a strategy called the two-pointer technique. And this strategy is mostly used with linear data structures like arrays and linked lists, for example. And this is particularly useful when we need to find like a pair of elements within a linear data structure, for example, that satisfy a certain condition, right? Which suits our case, because we need to find a pair of elements which creates the largest container. And the way it works is the following. So there's many variations of this two-pointer technique, but the one we will apply here is that we will have two pointers, a start pointer and then an end pointer, which will be at the last index, right? This one will be at the first index. And this might look familiar with the sliding window also technique. The big difference is that here we're just looking at two pairs of elements. We're not looking at the range of elements that's um, within these two pointers. And also, like, we're not dealing with finding a subarray which satisfies a certain condition. So the logic, of course, with this technique is to figure out how should we move these pointers, the start pointer and end pointer, such that we find this pair, or we find this maximum value, right? So in essence, we are also dealing like with a greedy algorithm, and I will explain why, right? But primarily, I'm going to show like the greedy part in a moment, but we can assume as well it's greedy because we're trying to like find a max, right, of something. Um, okay, cool. So the way the solution will work is the following. So we start at the first iteration we have these two values, the height 1 and 7, and then we will compare. Is 1 smaller than 7, or is the start pointer smaller than the end pointer? If it is, we will basically move or increment the start pointer by 1. So then in the next iteration, the start pointer will be here at 8, and 7 will stay fixed. The end pointer will stay fixed. In the next iteration, we do the same check. Is 8 smaller than 7, or is the start pointer smaller than 7? Right. This is our new S. And actually, no, the start pointer is larger. So in this case, the end pointer will decrement, so it shifts to the middle of the array, and then the end pointer will now be here. So we can cross this out, and that will basically, and of course, we will compute the area, etc., as we previously did here through every step. But that's with the logic that we're gonna basically move our pointers. And the logic of doing this, so let me just illustrate it more clearly. So in the first iteration, right here, we saw that 1 was smaller than 7, right? So the reason why we move the start pointer towards the middle, or we incremented the start pointer, was because I mean, we could like safely assume that perhaps if we move one value to the right, that will be a larger value than the previous one, right? The previous one. Um, and in this case, for example, in this example, it does like make a lot of sense because 8 is larger than 1, and then these are the two pairs that actually got the largest area at the end, right? These two pairs, which correspond to this 7 and this 8. So that's basically the assumption. So that's the greedy part. We're always basically trying to max it out in this way, right? So that's like the greedy part of the algorithm. There's also one more important situation that needs to be handled. So, for example, in cases where both elements are equal, right? So we have 1 here and 1. Of course, these conditions will will not handle it, right? Because we still haven't spoken about what happens if the two values which the start and end pointer point at are equal. So in this case, we have to move both of them at the same time. So in this case, we will decrease, right, the end pointer, and here we will increase the start pointer, right? So here we will have our new start pointer and end pointer. So that's the main logic for this. And then, of course, in terms of the time complexity, as I said before, this is going to be big O of n, so it's going to be linear. And in terms of space complexity, it still will remain constant because we're not like using another auxiliary data structure to store the results or well, not the results, but any intermediate computations. So why is it time complexity linear? Because basically we are iterating through this whole array only once, and the iteration will stop once we reach the end of the array, right? That's why it's linear. It has to go through each element only once. Okay, so let's start right now the implementation. So we're gonna initialize our end and start pointer. So let's do our end. So length height, and then our start pointer is at 0, and then our end pointer is at the last item in the array. And then we also need our variable to store the maximum amount of water. We can call max water, and we can set it actually to the minimum value, negative infinity, that we can pass it in like this, negative infinity. And then we can start basically iterating through the height for, we don't need actually the I index, for, and we have range n. And so the first thing we need is to grab the minimum value, the minimum height, right, between the pairs. So height, and then we have this min, and we will say height start p and height end pointer, right? So if I take quickly this example here, this is going to take the minimum between 1 and 7, and of course it's going to be 7. Sorry, 1 will be the minimum height. Cool. And then we have to compute the base, and that will be the end pointer minus the start pointer, right? So in this case will be, so we have 0, 1, 2, 3, 4, 5, 6, 7, and 8, right? It will be 8 minus 0, so the base of course will be 8, and then we will have the area. So the area will be the minimum height we got times the base. And of course, we need to update this max water variable. So we are going to say, okay, give me the largest between the current computed area and the current max water. And in this case, our area is 8, right? And then of course, 8 is larger than negative infinity. So then max water will become 8. And that's how it's going to be basically updated through each iteration. And now we have to move or define how our pointers are going to move. So which I already explained previously, the logic. So if we have our if this height is smaller than the one at the end, right, the other pair, we will move our start pointer by 1. Then if it's the opposite condition, right, so if our height, or sorry, if our, well, let's leave it there. But if our start height is larger than the end height, we will basically decrease the end pointer by 1. So it moves inside as well. And if they're both equal, we will move both at the same time. So we will increment the start pointer and decrement. I submitted it by mistake. Happens a lot. I have to find, yeah, the combination of the short key later on. So I don't do that. Okay, so start pointer increments, end pointer decrements, right? And then we return the max water on that we found. Okay, perfect. So everything looks good. Start and end. We have this base here, the area, the max water, these conditions here. Okay, perfect. So let's run this. So yeah, these test cases are passing. So let's just write some other ones, which, for example, here everything is equal, and then we can like do some other cases here. Let's run it. So yeah, the algorithm is behaving as expected, and also in fact, like technically, since we don't really need the index, we should, I mean, we can leave the for loop, but since we don't since we don't need the index, we could just use the while loop, right? So we can say while the start pointer is smaller than or equal to the end pointer, we basically do this iteration, right? We keep going. Um, oops. So let's just make sure, yeah, everything is working as expected. Yeah, we can remove this. This is basically the solution. So it's also very simple, but yeah, I mean, it's quite elegant as well. So let me just submit this, make sure our solution passes all the test cases and everything is working as expected. Um, okay, perfect. Yep. So um, that's the solution. I hope, yeah, I hope all the explanation was quite clear as well.